My name is Stan Tomov. I'm a research director here at the University Computing Laboratory at the University of Tennessee in Ohio. I'm part of the linear algebra group that is headed by Professor John Bongara, and maybe many of you know him. He's one of the founder and maintainer of numerical linear algebra libraries like PlayPack and ScalarPack. So today I'm going to talk about how to do linear algebra in parallel. So that's a very complicated issue, of course. So you will do everything from here, but at least we will try to just touch on certain topics, see what challenges are, go over some algorithms, see some ideas. And there will be briefly a few slides on a full tutorial about using one of our software packages that we developed here at the University. So this is the outline. So I will start with a brief introduction, and then we will go through a brief methodology of how to develop these algorithms. When we develop linear algebra libraries, these are based on the BLAS interface. Maybe you probably know these are simple vector operations and dot products. These are like level BLAS. Then there are two BLAS, make it vector products, and then make it products in level 3 BLAS. And what we're interested is in developing higher level numerical algorithms and use the BLAS interface. So layers in particular, we would be a sequence of BLAS code and also higher level non-linear problems like eigenvalue problems, again, sequence of BLAS code. So we'll go over some methodologies of these architectures. The GPU algorithm, currently, what is interesting here is to solve the execution of these algorithms dynamically over all available hardware resources. And talk about Magma, and recently we started some sparse linear algebra computations. These are all very important, very high interest, and also very challenging to develop in hyperforce. And you will stop me at any time to ask questions. So major challenges to software. Basically, everything that we do is motivated by hardware changes. As hardware change, we will adjust our software to use that hardware efficiency. In particular, we always want to be very close to the machine speed, correct machine speed. So we are at a time when the design is drastically changing, and this forces us to think and redesign our software for, in particular, today's heterogeneous architecture. So this would be a combination of multi-cores and certain accelerators like GPU, or Pi kind of change, and in particular, these legacy libraries that I mentioned, PlayPack and ScalarPack, these were designed for the new architecture, so they have to be redesigned in order to be efficient in those architectures. Just briefly to give you historically how this trend has forced the change in software. So, for example, in the 70s, the linear library was LinPack, and this was very efficient for machines at that time. It was designed for vector machines to do vector operations. Is when some machines appeared with the hierarchy of caches, algorithms had to be redesigned. Alright, so these algorithms mostly work on level 2 of operation. So blocking line on a well block that usually is bandwidth provides. And operations that would be able to use this memory hierarchy that was in the machine at that time. Then it was scalar type that moved scalar type to distributed memory system, and the appearance of multi-core we start here to like plasma in particular. This was started in just multi-architecture, and after that we started Magma, which is a library to target heterogeneous architectures and adding accelerators GPUs. So it's briefly to highlight what are the challenges of modern architecture. So many, but the main two, these are the explosion of parallelism. So even using, for example, a single GPU like K40, this has 1,882 cores. So naturally, if you want your code to run fast on architecture like this, you better write algorithms that require that much parallelism. So a very big level of parallelism that is required by the algorithm. The second one, this is the growing gap of compute versus data movement capability. Basically, hardware vendors know how to make the processor fast, but a big challenge is how to feed those fast processors fast enough with data so that they don't idle. And this gap of how fast we compute versus how fast we can move data has been growing exponentially over the years. And now it is actually the thing that we can see from this graph. We have the performance of a compute-intensive kernel. This is the unemphasization dense matrix K40 GPU. So the curve on the top, this shows the performance of this architecture. So it gets to about 1,200 gigabytes this computation. So it's operation and it is compute. But now you look on the left, what happens if you try to use the same hardware for sparse operations, and these particular memory bound. So you will be able to load some data in the fast memories and use it many times. Basically, it's something and you use it just for one computation and you move forward. So this would make us you can move data. And performance here actually you can see that just a very small fraction of we get from this architecture from this particular operation. So on the right, we show the performance of a sparse matrix vector. So you see this memory bound operation here is just about 20 gigaflops. So this is what you can extract from this powerful CPU. Of course, they're highly optimized, so you cannot go better than that. They have reached their theoretical bound for memory bound computation. So it is optimized, but that's what you get. So the new algorithms are needed that would reduce data movement, and we would see this both in density algebra on the left, although we are getting the performance now that we expect. Still, in order to get to there, I'll show what type of algorithm we could use. We will also discuss that basically you see this discrepancy. It's very difficult for sparse computations to get the high performance of hardware. people work there on better algorithms, for example, multi-grid type of things and stuff like that. He's mostly concerned about how efficiently the hardware is used, what type of flows per second you are going to get use the hardware. So moving forward, as I mentioned, we have to redesign these algorithms, and in particular the redesign for LAPAC that we're planning now for GPUs is Magma. It stands for Matrix Algebra for GPU multi-core architecture, and it is the LAPAC and LAPAC on hybrid architecture. This is the concept of the library. We support it for various, for example, NVIDIA GPUs. Current release for that is 1.4.1. There is OpenCL, that is Magma in OpenCL. Provides support, for example, for AMD hardware and all kinds of architecture. And the Magma Mine for Intel Xeon Phi architectures, or sometimes with mine. These are the developers and the collaborators, so it's us, UCK, UC Berkeley, UC Denver, India, France, and Saudi Arabia, but mostly it's a community effort. So if you come up with a better algorithm and are willing to contribute it, that would be, we are always happy to take algorithms from the community and incorporate them in these packages. So, key features of Magma. Of course, we do this for high performance. Then we have multiple precision support. These are the 4 standard precisions: double, single complex, single zero, and we have several algorithms that use mixed precision also. All algorithms are hybrid in the sense that they use both CPU and GPU. Out of GPU memory algorithms, these are algorithms when a single problem is not fit at once in the particular memory. So that can string the computation to that. I have support for multiple GPUs. This is the same in another way, illustrating the high performance. For example, that was the first feature that I mentioned. So, as you see, state-of-the-art CPUs, in this case, we have 60 cores, processors. This is the performance that you would get with the MPL library at the bottom. So about 300 kilocores. If you add a single GPU, suddenly your performance is about 12 times. So that's significantly faster. Just add one GPU. Again, you see that it scales very well. And from functionality on the right, as related to CUDA and OpenCL and the Xeon Phi. So in general, we provide differences, trying to be as close as possible to LAPAC and ScalePack, and it's over, and I move forward. So the different topics that I mentioned as the key features. So one was high performance, performance. The second was multiple precision support. This is just to illustrate what kind of performances we get in particular for LU. You can see all performances are very well optimized, and in general, the complex performance is a little bit higher than I think the real precision performance, because intensity is a little bit most recent Kepler GPUs, for example, this has changed. The rate is about times. The Fermi, so this was the Fermi, the rate was higher, I think it was different single and double. And this is what actually motivates us to those mixed precision algorithms that I will also later. Now going to the methodology overview. So very briefly for now, we use hybridization methodology. This is what we call when we split algorithm into tasks. As mentioned before, our operations can naturally be split into a sequence of block calls. So we split these even into smaller ones. And in general, you would have an algorithm where there would be a critical path, operations in general that are very difficult to parallelize. And so the parallel move that work. And then a path, then you have three and usually it's data part. So our with some tendencies and properly schedule the execution of the available hardware resources. In general, what will happen, the critical path would get scheduled of the CPUs because it's not that parallel. The data parallel computations, in general, matrix multiplications, these are scheduled on the GPU. This we will see how it's successfully applied to the main linear algebra algorithm. Going a little bit into more detail, what are these hybrid algorithms? This is a simple example of how you can do to implement hybrid algorithms. So in this case, I'm showing the representation. If only in black, these would have been the LFS. When the line is in red, this is what makes this code hybrid. In particular, what we do at line 4, we say magma get matrix a simple. This is a small part of the matrix from the view and send it to the CPU. Basically, data of the GPU. Now we have something on the critical path here, and we want to take this to the CPU and compute it there. So this is what line 4 is doing. So say, okay, this will be on the critical path. It to the CPU. Then we continue up control the path to the VGEM. This starts the computation on the GPU of this matrix multiplication. The draft next, so line 6 is not finished, but it is up control, so it goes to line 7, and all this flow down on the CPU. Just when very magnet VGEM, this is more like a request of the GPU to do a matrix multiplication. It's on the CPU, so the CPU goes on line 7. Now we want to make sure that the data that the right that is sent on line 4, so that's we can a sync. If the right, then we continue on line 8, which is doing the path on the CPU with standard code from LFX. When LFX finishes on line 11, we send the result back to the GPU. We make sure that the GPU has received it on line 13, and GPU continues with its execution with that data. So just simple, in this case, with static schedule, you get very high performance that I illustrated before. And so what happens is here, thematically, critical typical path that we do on the CPU. We have 16 algorithms that basically you can do the CPU work totally overlap with the GPU work. And so all algorithms like the one-sided optimization at the speed with which we can do modifications. So I'll go over the different items, but because I have a lot of slides, just to maybe cover some straightforward topic first, I will jump to this short Magma tutorial first. And so, time. So, just very briefly to go over some topics here. So you would have the slides, you can try them later if you have time. So just install this package, how to use it, and I'll show two examples how to solve a linear system and how to solve an eigenvalue problem. And follow the general example. Usually on a new system when we put up software running and make it product with good exercise with benchmark. So do you install the laptop? Yes. These laptops so sometimes on Google depends what card you get there, but we support to install it in and I will with you. So install me, you just get it on the Magma web page. So you are the latest Magma 1.4.1. You can say this one. You select the library. It's to use Magma is to install LFX, BLAS, and the CUDA toolkit on machine repair system administrator. Just load those from some modules to be already available there. On my it's I think it's also by default there. Then you have to do is just modify this making file where few you have to change. One is to say what GPU you have. So this is the GPU target equal or Fermi or other packages, maybe mice and things like that. And then you specify your effect. For example, ML root in this case shows where LFX is installed on the Intel library. And the CUDA directive. If you are on a large system, this is maintained by system administrators. Downloading these or loading some of these modules, you can see environment. Sometimes the environment variables that point to those. For example, on this particular system, when I was playing, it was in this variable tray to the toolkit directory. So this is what I will put there, and just make and go and to create the library. The new file for more information. So provided to the Magma user forum. This is if we have a lot of questions there. Sometimes we will answer each other. That's a snapshot from there. The documentation on the internet. So this is done Oxygen. In Google, you can just type, for example, get underscore GPU and line that counts this from our documentation. Then you click on it, then you get and just constraints, and it is very similar to LFS. Even I find it useful sometimes when called because actually immediately will give you the order of the argument and this documentation, so you don't have to look for it in the package itself. This is the Magma convention about names. You have to solve a linear system, for example, that you don't know how it's called. This may be so. Usually, we would put a prefix at the beginning, magma underscore or magma plus underscore, and then it's followed by the precision. So B, for example, is for double, X is for single complex, D or mixed precision, double plus single. B, C is double complex and single complex. Other than the ones these are the main types. So in general, the corresponding complex. And this is followed by the operation that the routine SV is for solve, for example. If you want to solve a linear system, PR angular factorization, QR and so on. The writing value problem, the general. And again, this is followed by for example, underscore GPU. This is meaning that both the output of the matrices that we are giving to this routine are on the GPU memory. So if there is underscore GPU, that would be the typical LFS call where you have done as you do to call LFS without knowing anything about GPU, automatically would offload into the GPU. So similar functionality, for example, is provided from Intel for their package, their translation of MTL hybrid systems. They call it automatic upload. Don't specify. The main convention that this functionality, just so that there is this link, you can go and all the links of the functions that are supported. This if you go on that page, it's something that very deep in the guide. It's a 2-page document. Okay, so now solve a linear system of equations X equals B. What you have to do is just include those files, magma.h and magma.h in your file. Somewhere you should call my name, and then this is how to allocate memory. Sometimes this core pin is used for faster reactions. So this is how you allocate memory, and then is your matrix. In this is the matrix HA. It's on the host. It's in where you want, but then you at some point you command get array and the matrix. This factorization that we are compatible with any LFS code that you may get. After you obtain the LU function on this matrix A using the GPU, you call LFS, for example, to solve those angular matrices. You can download the library in the testing and testing underscore
only one on the CPU, because you specify the underscore.
I would use the GPU, but visual memory starts from the CPU. So that's the only if you set underscore GPU, this routine would expect that argument, in particular H8, is going to be GPU. So you have copied that before to the GPU. It's useful when people will comment all down GPU, so effect is there with all but for easy translation of scientific codes that were using Caliphate before, that would be the simplest way where we internally would do the data copy. So the GPU doesn't know anything about the GPU, but
memory. What if you're trying to work with a array that are too big to fit into the memory of the GPU card?
Yes, it's a good question. So when I go back to Algebra, I will show one example of this type of algorithm. But it's possible.
So this assumes that
not right now. We support algorithm does not require. So kind of split computation through memory. We will query how much the GPU memory has. Right now it's set to not exceed that 2/3 of it is. We have to be this as with the user. Next example is solve an eigenvalue problem. Again, we have to have the following definitions. We call again block many, some memory locations, and then we're to LFI routine for solving eigenvalue problem. And you see this our library, so may top level have generated those so as I mentioned, it's very useful just to see how powerful you're using. So that's in testing biggen, for example. If you are with minus cell, minus C to run cell is for LFX, in this case the CPU code to better performance. So you can see here when I click these options, it immediately tells the case of the machine that I have. Obviously, I have very powerful use of the CPU. At 3000 by 3000 matrices, they have only 11 flops per second versus the CPU, the GPU, they get 100 times faster. So this is for benchmark. Typically, we will give to our students some examples of how to write simple codes. One example is just to give them a MATLAB code. That's what is given on the left there, MATLAB code. So it's a sequence of calling matrix multiplication or other parallel routines like QR. Basically, in this code, so if you have this code, the simple exercise to write the type of code is form the GPU. If you look more carefully at what this is doing, actually the most compute intensive part of this code is when you layer G equals Q transpose times Q. So it's a code that will do QR factorization very solid. You can think like, let's say, million rows, let's say, stuff. So this is for this operation, we compute this G for Q transpose times Q. A hybrid code would just place on the GPU, have this small matrix, only 36 by 36, and to the CPU and do all that complicated code that well. We have SVD, no need to support singular variable contribution with GPU, do as on G or CPU using Califax. It gives very high performance. So this is another example that you can find with the manual, even if you don't have the time to try it person. This is how your code may look like. So for multiplication, Q transpose Q, you have some kind of cupola, agent, or digit, whatever perform precision you use. It would be some piece of data. So after you get the G, you have to have a cupola, get or whatever you use the CPU. You get the CPU data, you use Califax. After each data will move back to the CPU. So if there are no questions on this, I may just mention here again, we take contributions. There is a guide. We follow the LFX programming style that is there. I mentioned the naming conventions and the design, so we use blocks. Usually don't like algorithms where somebody will unroll and start using blocks calls, so provide things that are not specific blocks. In general, our routines are developed in double compress, and we think that precision to generate. Decisions are determined as magnitude. These are provided. This would be multiplied neighborhood B, which is different from that routine, which is the typical for LFX. The length between C and C++, we provide wrappers for okay, so I will go back to methodology and go over some of the other algorithms that I mentioned as parameters. One type of algorithm that we are so-called mixed precision refinement algorithms. In these algorithms, we use the fact that single precision is not better than double. But we share is performance for various sizes. If you solve a dense even double precision, this is the end of the bottom, so you get about 300 gigaflops on this area. The problem is single is double, so it's 600 gigaflops. Of course, that's exactly the single. So now what we do is we need to refinement codes just run this simple retracing operation. So find the solution xi plus 1 is the old plus the residual times some kind of preconditioner. In this case, we take the preconditioner to be based on LU factorization in single precision. So LU factorization in single precision, and this is the level of computation in this case, is the curve for 600 gigaflops. Do just a few iterations to raise exactly double precision. So that's what the other curve in red is does not always work. In particular, this operation LU in single precision inverse makes sense. This means at least your main singular in single precision. So the number should be in general less than the 8. If it's higher, we can that is at runtime and just move to the more stable algorithm. These are the mixed precision solvers. Now the question about what if the matrix is too big. In this case, we cannot more than 24,000 matrices. If we want no problem to go on the GPU. If we put the entire matrix on the GPU, that's good to minimize some communication. So, and we all want to do that. Too big and it doesn't fit, then we have to develop new algorithms. And indeed, we developed some that allow us to extend and be able to solve beyond that limit. And as you can see, performance remains at that positive high level, although we do more communication.
The 24,000 is that single or double?
I think this was in double. And these are the yes, I did say so much now. So you can get by memory. You can solve like 40,000 to standard if you and square this in double precision. So how the algorithm moves, right? So when you do factorization, you always start from the top left corner and you start factorizing. So you're doing LU, you do some transformations with 0 elements below the diagonal, and you of course can apply them. So what we do for this algorithm, we take a big panel from the left that puts it on the GPU, and we barely just run the standard algorithm. So the standard algorithm is only factorization of the GPU part. When it's done, it will be just copied and send it back to the CPU, and the GPU will take the next big panel that is, in this case, it's good panel. Before you do the LU factorization of this, now we have to apply all the transformations that were done on the green one. So the step would be to take block by block the factorizations from the green. They would be just small, so they would not increase the memory requirement. Bring by one to the GPU until are applied to the blue part, and do the standard factorization on the blue part, and then move back to the next until it's done. So that's actually what algorithms can keep you. It was called their core algorithm. This will apply in cases when your CPU memory was too small and they would use the big memory. But the sequence of operations is exactly like that. And as you see, it works very well. Its hierarchy here is different. Here, we're saying, okay, the GPU does not have enough memory, so we use the floor memory of the CPU. That in case was the CPU memory was not enough, we would use lower memory of the CPU. Now about multi-GPU support, so if it's on a single node, multi-GPUs on a single node, we just want the block 6 distribution is the best. So you would get a chunk of the data and this is what it will work on, then GPU 1, GPU 2, and then the cycle. The GPUs take their part and GPU take another. The guarantee is that as you go with the algorithm and have kind of balance of how many work on the remaining problems, because take it one by one. Generally, you can guarantee some kind of balance of the remaining. And this creates the nice performance and scalability. That was this from the time when the 2090s available, and this was in Finland, and then the Kepler came. So that's to illustrate that the single Kepler is to this operation to here than 2090. So it's about linear solvers. We have done a lot of work on eigenvector problems. So these are problems of the form of AX equals lambda x. So you have a vector x, and the good way to apply the matrix is just in the same direction. So the question is how to find those lambda and x. Questions are complicated here and outside of the scope, so I'm not going to talk much about this. There are a lot of applications. As you can see, I have just mentioned a few, so they're very important problem, and many people need those. They need to solve them as fast as possible. And we have done it for various cases. This is just some recent work, the non-symmetric problem. Solar problem, you can see that it's breaking into main pieces. So usually what you would do in this problem, you would optimization of the main piece to bring to an easier form. In this case, you have to bring to up second form. So this is having all the diagonal is 0 above the subject number. So it's easier to solve, and basically to get to there, you use orthogonal transformations. Orthogonal transformations does not change the eigenvalues of the mu. That's why when you find eigenvalues, reduce them, those would be eigenvalues of the original one. Also, when you find the eigenvector of the reduced one, you can find very easily the eigenvector. The operation of the secondary spectrum in this particular case, so for our iteration, bring it by angular form, that values on the diagonal, and back transform to find the eigenvector. So just to show, we've done a lot of optimizations on the different parts of the code. So currently, using GPU, we can accelerate, for example, LR back on a CPU about 4 times a single GPU code. And it's important that whoever is interested to read more, for the symmetrical also did a lot of work. So this performance is just using CPU. In this, it's Intel port like that. This is what you then add one GPU green, accelerates scales after that, 2 GPUs. And then a major challenge is to use the communication result. So all these implementations so far here were just the algorithm with optimization for GPU. It is very good performance, but then it to modify the algorithm that uses less communication. As you can see, the improvement in speed was much higher. So now a single GPU instead of being there about 12, you can see that it's just about 200 or so. So about 3-4 times higher performance. Yeah. So in part, these algorithms go from the basic to govers advanced. It can be very fast. And second stage that is going from advanced to trial. If symmetric we go to Kettenberg form now because of the symmetry, the zeros that we evolve in the zeros about the dynamic form. Now a few words about current work. We are trying to use dynamic runtime systems that will work. So these are typical phases. I don't know if you have seen phases before. What it shows here is a single shows a single thread when it's working or not. The phases are inside. Let's say you have an algorithm that is in blue, and you have to schedule this on the available port. You do something like this, but then you wait until everybody finishes, and then you start your part of the algorithm in yellow, and so on. So dynamic runtime system is very likely to merge this naturally. Basically, you automatically go evencies are not allowed. So in this case, you can see the next phase can have significant reduction of the so that's the x-axis. Then if it's all automatically, the runtime system is scheduled without violating the So we are moving towards this type of schedulers in Magma. Basically, this should simplify the code. Let's say you have a code like this, which is sequential. If you would run this sequentially and go in the protocol and instead I insert those routines into some kind of runtime system. So single thread will go through the sequential code and not execute them immediately, but just put along with their data dependencies runtime system in the background, and that system will schedule all those without waiting the data. So do is just say which is simple, which is output given, the type system will take care of. So try, for example, these schedulers that are on the right. Example of how these places look like when we use the Quark scheduler with multiple GPUs. As you can see, this is the case of 6 GPUs. As you can see, there are no white spaces, nothing beside all. Very tight, so you also get very high performance with that's for E on KPC GPU 1, 2, 3, 4, 5, 6. So on system you get up to this very performance 5 per second. Sometimes it's difficult to imagine how fast. You think for, let's say, you are to run sparse, there was also something. That's also the machine speed. So machine. Then work on it. Again, very good result. This is the that on the left, the section on all gigaflops taken using 1 core, 2 cores, up to 9 cores in this case. And there were 3 cores linked to 3 GPUs. So all compared to the peak as whatever we could have gotten from blocks only, we 75% of the peak. If we move it, we get perfect scalability, we get 75% of peak on 100 nodes. To conclude the discussion on bands where we get very high performance. So recently we started also work on sparse linear algebra, and I'll just go over some ideas that we're looking through. So that's sparse arises naturally in many simulators that are called to PDEs, for example. The current, we are putting these in a package called Magma Sparse, or subpackage. Magma is Krell, subspace, iterative linear system solvers, and item solvers, support for various matrix formats, kernels, block kernels, and various building blocks for precondition. That's just a slide from before to highlight again what is here for engagement. So what we want is to develop algorithms that feed these memory bound limits, 20 gigaflops. So we're looking for algorithms that do that. Example is if you have multiple vectors. So if you multiply a sparse matrix times a dense matrix, one the sparse matrix in your fast memory, if there are algorithms that can use multiplication with multiple vectors, then you can use that matrix to multiply all the vectors. And result this is what you get. So this limit in green, the 20 gigaflops, and we jump, we exceed this memory bound limitation. So algorithms that can be redesigned to use kernel in the CSV style, for example, above 100 gigaflops per second performance. So that's very good. About this, so we called it, and it is very easy actually to code file subspace method. How the algorithm look like in this, usually every line there has a corresponding block called Q block. So let's say Q block DAXP is the first matrix. So codes are very easy to develop. So we developed several codes, like 2G, 560, step, conditions, and more about the computation volume. We did some optimizations. So sometimes you need one vector in one operation, then you have to go over it again to do like a total or something. So we have optimized versions that virtually just reduce. Sometimes you get speed 2 times from so the modified code would look like. Now, in the area of linear algebra, there is a lot of interest in the so-called communication avoidance algorithm, level subspace method. And this is one example of the communication avoidance VMware. So the way this minimizes communication, you build up your parallel subspace times after R, A to R, and so evolution in that space. So the idea is to have its power kernel uh, uh, to reuse some of these data to load your matrix A1 in fast memory, multiply with the vector 1, and get the resulting vector and apply again and again several times. So this result that we have recently, the left, based on any vectors we group together, we give some kind of acceleration. So in this case, you get acceleration of 16%, and we group in this case 5 of those vectors together. But then combined with other optimizations that are possible in this algorithm, in particular the optimization, get an overall improvement in this case about 2 times. So that's very good. These are speeds for one particular method. Again, 2 times acceleration, but again, that's to look for comparison again. Optimization that we did here, which actually accounted for most of the acceleration, was the optimization. In particular, we did this mixed precision to SQR. So SQR obtains plus performance. So, but the error is bounded by the square of the transition number of the vectors that you are orthogonalizing. So that's a well-known algorithm, and it is known that it's not stable. But what we did is use very high performance characteristic for level 3 plus, but we managed to remove the square here from the numerical instability by selectively using double execution, and in this case double in particular place. And what we also do is we can indicate what precision we use. We must have those to make this transpose time. The input for this makes it in standard precision, and generally it is supposed to be memory bound because they are very long. When you read them in your fast memory and start multiplying them, but what we do is replace that accumulation and higher precision. So maybe is obtained to higher precision. In this case, they do cholesterol consolidation of the small matrix down. Doesn't matter how slow it is because the matrix is very small. And then we have this backward substitution for Q, which gives us this QR optimization. V multiplied from the right to the universal arm. So that algorithm gives very high performance. Now, if somebody wonder when we need the kernel that I mentioned, sparse times dense matrix. One example is eigensolver. So in particular, the LOVG method is set for locally optimized block PCG. This sets the smallest eigenstate using the block algorithm. So it is either sparse matrix of dense block or dense gem operator. On the left, we have again this optimized sparse matrix. This one is used in the algorithm. And as you can see, if we get there from the basic kernel to about 100 gigaflops, overall for the algorithm, we have to do a little bit more. And typically just for 32 vectors, but all because the algorithms using nature of the algorithm using a lot of matrix multiplication is double the performance. So get to about 200 gigaflops using GPUs. The CPUs that you can see here, originally traveling slightly, but still and see limit 10 times speed up, the enormous speed up that is the single CPU compared to the CPU. It's not just single CPU that stated so sitting core send it in parallel. Then we did some other linear algebra. These are building blocks for reconditioners. I will skip that. There are just some references for whoever wants to read some more. Some of our future directions cover good distributed. We have our currently working distributed. We have some examples with communication generate. I'll do is incorporate more scheduling here, partitioning, in terms of tuning, data tuning, host tuning, and to extend more the current functionality. Next to the material, which we already covered, and basically that was my last slide. Thank you for the attention. Time for questions.